So what we have observed this much so far is that there is a lower bound that we found, which is omega of g, the click number, and an upper bound which we found, which is the delta of g plus 1, which is the upper bound for the chromatic number, right? So the chromatic number is between these two. Now we can ask many questions, right? When is this lower bound attained? This is an interesting question. There are several classes that we know attain this, but we still don't know universally when. Then can chi be much larger than omega of g? Okay. I mean, like so we know that the clicks will make the chromatic number large, right? If you have a large click with let's say t vertices, then we need at least t colors. Right? Now, can you have t to be small, right? The complete graph omega to be small, and then make the chromatic number much larger than omega, right? The click size. So because in the case of odd cycles, right, the delta is just 2, right? And, but that doesn't say that for very large numbers, chromatic numbers, we can have this property. But is it possible? So here is an interesting result, which says that we can have graph without triangles, okay, where the chromatic number is as large as we want. What do you mean by triangle? Triangle is 3 vertices which are adjacent to each other, which is the complete graph on 3 vertices. Now, if I have several vertices, and if there is no triangle, then I cannot have any complete graph more than complete graph on 2 vertices, an edge, right? Because if you have any larger complete graph, every vertices are adjacent, so therefore you will automatically get a triangle as a subgraph. So when there is no triangle, we know that the click number omega is going to be 2, right? So what we are saying is that we have graph with omega is equal to 2 and chromatic number as large as you want. And how do you do that? Okay. So of course there are many ways to do this, but one famous result was this construction that is given by Mycielski. Okay. So Mycielski constructions shows that if you are given a graph which does not contain triangles and has some chromatic number, let's say k, then I can make a graph from this graph, right, a new graph, whose chromatic number is strictly larger than k. In fact, it's equal to k plus 1. And there is still no triangle. So I start with a triangle-free graph. I make a new graph. The chromatic number increases by 1 without creating triangle. So therefore, I can keep on doing this. So I can make the chromatic number larger and larger. So what is the procedure? So the procedure is the following. Okay. So given the graph, so here is a small example, right? So given this graph, I take the graph and keep it as it is, one copy. Okay. So I keep the copy of the graph as it is. Now I make a duplicate of every vertex. Okay. So duplicate of vertex means that so there is a copy of V1, right, which I call U1. There is a copy of V2, which I call U2, etc. So I make these copies of this graph, and then I make the neighbors of U1 are precisely the neighbors of V1. Okay, so V1 had the neighbor V2, so therefore U1 has the neighbor V2. Right. U2 had neighbor, V2 had neighbor V1, therefore U2 has neighbor V1. Whatever is the neighbor of V1 in the graph G, that same vertices are going to be the neighbors of the corresponding vertex here also. Okay. So now whatever graph I get from here, finally I am going to add a new vertex that is called W, and W is adjacent to all the new vertices that I introduce. Whatever is the number of vertices here, I am going to make W adjacent to each of them. Okay. Now UIs form an independent set, right? That is immediately clear because you can see that UIs there is no edge between them because they were not neighbors of any of these vertices, right? Before, right, in the graph, in this graph. So therefore, they form an independent set. So when I add W to these guys, this is not going to create any triangle because if it creates a triangle, there must be some edge here. Now similarly, there was no triangle in this graph. So now there is no triangle here. Now can this create a triangle, right? Now U1 is adjacent to all the neighbors which were copies of, the neighbors of V1, right? So if I look at the graph with just U1, this U1 cannot be part of any triangle because U1 is precisely like V1 in the graph, right? If I look at just the graph V with the addition of U1, if there is a triangle involving U1, there is a triangle also involving V1 because that is the triangle in this graph only, right? Any triangle here is also a triangle here. So this is true for every single vertex, and because there is no edge here, we don't have to look at two of them together. And therefore, I show that this graph is triangle-free. Right? So I get a triangle-free graph by doing this. And then, now I want to show that the chromatic number also has increased by 1. Right? Now, how do you show this? To show that the chromatic number is increased by 1, we have to first show that there is a coloring with one more color, and we have to show that there is no coloring with the chromatic number of G many colors. Okay. So how do I do that? So here is an idea. Let us first show that with K+1 colors the coloring is possible. That is easy, right? Because I start with a coloring of the graph G, right? The first graph that I started with. Now whatever is the coloring here, each vertex, let's say Vi has some color, I use the same color to color Ui also. Now because there is no edge between Ui and Vi, I can give the same color here, no problem. And this color, of course, is okay to give because this vertex is adjacent to only the neighbors of V1. And V1, I have given this color C. That's the color C, right? And because all the neighbors of V1 gets different colors, right? Other than C, all the neighbors of U1 also get a color difference. So therefore, U1 will not create any problem with the coloring. Right? So this I can do for any UI. So therefore, I will get I can use VI, the color of VI to be equal to the color of UI. So I get all these vertices, the same color that is happening here. And now for W, I give a new color, right? The whatever is the chromatic number plus 1, right? So one more color I give, and that new color is used. And because it is a new color, it will not create any problem with any of the existing colors. And therefore, I get a proper coloring with one extra color. Now we want to show that by there is no coloring with chromatic number of G many colors, right? So let's say that chromatic number of the graph is K. Then I want to show that there is no K coloring, right? Of the new graph. Now, why there is no K coloring of this new graph? Suppose there is a K coloring. So we will start by assuming that there is a K coloring of this new graph. Now, suppose there is a K coloring of this new graph, then it uses this K colors, at most this K color is 1 to K, right, on the vertices. Now, given any coloring, okay, so this is one property of coloring, right? Given any coloring, let's say using, let's say color red, blue, green, etc. I can always change the names of the colors. I will say that all the red vertices now I am going to call as new green, okay, and all the green vertices in the original graph I am going to call as red, right? So I just change the names of red and blue to each other, right? So red is now the new blue, and blue is is the new green, and green is the new red. Right? So this is just renaming the colors. It does not affect anything about the properness of the color, right? Because earlier it was called red, now it is called blue, or green, whatever. So therefore, I can always change the names of the colors as far as I change uniformly everywhere, right? All the red I change to green, and all the green I change to red, right? Then it is okay. So therefore, we can assume without loss of generality that the vertex W is colored with the color K. Just to make the argument easier, we don't really have to assume, right? So we will assume that the vertex W is colored with the color K. Okay. So here is a better picture, I think. So we have this graph G and U1 to UN, and UI is adjacent to all the neighbors of VI also. So UI and VI are basically clones of it, exactly the same vertex, just one copy of VI. And UIs are independent, and then W is adjacent to all of the UI. So now to show that there is no K coloring, I will assume without loss of penalty that W is with colored with color K. Now because W is adjacent to all the UIs cannot be colored with color K. So therefore U1 to UN must be colored with colors 1 to K minus 1. Right? This must be the color that is used on UI, because K cannot be used on UI. Now if 1 to K minus 1 is used on UIs, I claim that I can use the same 1 to K minus 1 to give a coloring of G also. Why is that? Because see, UI, whatever color is for UI, that is adjacent to the vertices here, right? So the color of UI is not going to be used on the neighbors of VI, right? Because UI and VI share the same set of neighbors. So therefore, since UI is given some color, whatever color it is, that color can be given to VI also, because the neighbors will use different colors, right? So this I can do for every UI, which means that the colors used here can be exactly used on the colors V1 to Vn also. But this says that I am using just the colors 1 to K minus 1 to color all the vertices of the graph G. But G was a graph with chromatic number K, which means that there is no K minus 1 proper color. So this contradiction proves that there is no coloring where only we are using K colors. So therefore the chromatic number is at least K plus 1. And we already proved that it is actually at most K plus 1. So therefore the chromatic number increases by exactly 1. So we get a graph from a triangle free graph. We get a new triangle free graph whose chromatic number increases by 1. Now I can start from this new triangle free graph and increase the chromatic number again by 1. So I can keep on doing this. So I get larger and larger chromatic number. So this is called the Mycielskian Mycielski construction, and such graphs are called Mycielski. So given a graph G, the Mycielskian of G is the graph we construct this way. Take the graph, make copies of each of the vertices, right? And which means that exactly the same numbers are in the graph G. And because this is the new independent set, I make it a new vertex adjacent to W, and then I will get this new graph, which is Mycielski. So this is the construction. Okay. Now there is another famous result of Paul and Dirt, which says that we can have graphs with arbitrarily large girth and arbitrarily large chromatic. So what is the girth? So the girth of a graph is the length of the shortest cycle. Okay? Shortest cycle. right? So which says that it's not just triangles, right? We can make your cycle as large as you want. Okay, the smallest cycle is as large as you want. So there is not going to be any other edges connecting this, right? There cannot be an edge connecting. It will become smaller. So you will have all the cycles be large enough, right, in the graph. So as large as you want, you can make the smallest cycle, and then you can make the girth, the chromatic number also as large as you want. Okay. So this is using probabilistic method. We will probably not discuss the proof, but we will learn at least some of the tools that is required to work out these details. So this is a very, very old result of Politosh and very influential one. And you will see that this result, precisely this result that Herodotus used, Herodotus proved, was used to prove the addition, to come up with the proof for the headed name is this result was used to prove the headed name is conjecture, right? That I mentioned sometime before, or maybe sorry, I will mention it soon. So yeah, so this is a very influential result and very famous result, and it has so many applications, like on existential graph theory. So where you show that you don't tell you how to come up with a graph like this, but it will tell you there must be some graphs with this. Okay. Now a very important operation in graphs is called contraction of edges. So the definition is as follows. So given a graph G, it's a simple graph, and some edge, let's say u dash. Now what I do is that I take the graph G and delete the edge E. Okay, so just remove the edge G. Then identify the vertices u and u dash to make a new vertex. Let's say u star. So I am not doing anything to any other vertex, right? The adjacency remains the same for u. All the neighbors are going to be there except the one that we just removed, the edge, right? And for u dash, all the remaining neighbors are as it is. Now I basically identify this u and u dash, right, which becomes a single vertex. So all the neighbors of u other than u dash will be there in the new graph. All the neighbors of u dash other than u will also be neighbors of this new vertex. So I will get this new graph. So this is called the contraction of the edge. Okay. So here are some examples. So I start with this graph, right? I start with this graph. Then I find the graph G minus E by removing this edge that we fixed. So E is the edge, which is C and C dash. So I remove the edge E, I get this graph. Now I identify C and C dash, which means that C and C dash become the vertex C star. The neighbors of C and C dash, right? C had the neighbor B, C dash had neighbor B. Right? They will be still neighbors. Then C also had neighbor A, C dash had neighbor A, so C star will have neighbor A also. So after contraction of this edge, I will get this graph G. I denote it by G right slash E. Okay, so this is one example. So here is another example. So I start from this graph, right? I take the edge u dash as our edge to contract. So it means that I delete this edge. Now I identify u and u dash to u star. So of course the neighbors of u, which will be 4, neighbors of u1, which is 2 and 3, will be neighbors of this, and 4 and 1, and similarly 2 and 3 will be neighbors of u star. Right, remaining neighborhood remains as it is, right, and that's it. So you get G bar. So this is the contraction process. Now contraction is very important because we will not go into the details of minutes. That a graph, you start with any graph G, and you can apply as many as deletions, contractions, or vertex deletions also possible if you want. Then you will get some kind of graph from the starter graph. So these graphs that you can obtain by any sequences of edge contractions, deletions, and vertex deletion are called minors of the graph. So there is a huge area called minor theory, right, which studies like to classify graph based on its minors, what are the properties. Many important results have been proved using this. Okay, so there is a whole set of courses one can offer based on just minor theory, not one course, several courses. So it's a huge area, and I really have not looked much into minor theory, but it's a very interesting area with many applications. There are some few things we will see in a graph theory course in minor theory, like things like classification of planar graphs using its minors and things like that. So these things we will not discuss in this course. We can do this in an elective course on graph theory. So so I will not discuss minors for the time being. I just define this so that we need this operation to look at something else. So what is that? So given a graph G, so first thing that we said that what is the chromatic number, which is the minimum number of colors which which suffices to color the vertices of the graph such that adjacent vertices get different colors, right? Now another combinatorial question that one can ask is given a graph and let's say a set of colors. Let's say I tell you I am giving k colors because all the sets are like the sets of the same cardinality are the same for us. We can just assume that it is a set. Once you know the cardinality, you will just assume the numbers are from 1 to k are the colors, right? One number 1 to k are the colors. So given a graph G and a number k, I can ask how many k colorings, right? How many colors, how many different colorings of the graph are possible with using exactly k colors. Okay, so the number of k colorings of the graph G. Right? So this number is let's say chi of G comma k. Okay, so the graph G and is given, and then a number k is given, and the question is that what is the number of colorings of G using k colors. So for each k you can find this, and for general k you can write it as a function. So we can say this is a coloring function, right? If you assume k to be a variable or replace it by x, so then I will get the chromatic function of the graph. Okay. Eventually one can show that this function is always a polynomial and therefore it is a chromatic polynomial. It is a nice exercise using some of the techniques that we learned, but let us not go into that. So given a graph G, we want to find out the number of colorings, like proper colorings using exactly k colors. Now, my claim is that this parameter chi of G comma k satisfies this following identity. Okay, so given a graph G and any edge in the graph E, okay, we will assume that all our graphs are simple for the time being. Even otherwise, many of these things hold, but we will not work with that assumption. So, given a graph G and an arbitrary edge G, we say that the chromatic function or like the k colorings of G using which are proper is equal to the number of k colorings of G without the edge G, right, G minus E, minus number of k colorings of G contraction E. Okay. So like basically what it is saying is that the number of colorings of this graph, right, is equal to the number of k colorings of this graph is equal to number of k colorings of this graph minus the number of k colorings of this graph, right, using the same k colors, right? Similarly for any graph, right? So I want you to think about this and try to prove this identity as well. Okay, so why? So if you think about what is the proper coloring and what exactly happens when you take the contraction or edge deletion, you can immediately come up with this identity. It's not a difficult thing. Just you have to just think about what is meant by a proper coloring and what happens in G contraction E and what happens in G minus E, right? What is the difference between these two guys and what is the similarity between these two guys? Okay, so this will allow you to give a proof for this. Okay, so I think that is all we have for today, and we will look at a few more things in the next class, and then we will go to some other topics for this course.